Yeah, so for us, for me, it's quite a burden to speak after Ali because his presentation is always really good. But I think the presentation now will be very interesting and provides, of course, some insights of the topic simulation, what is really present at the moment everywhere. And as Florian mentioned already, the presentation is split between Markus and myself. So there will be a short handover in between. And just one word to myself. So I'm responsible for the all kind of technical questions regarding capacitors and resistors for Würth Elektronik. And then I think we will start with the presentation. So first, what is the basic, or what is the what is the thing we want to compare in this presentation here? So we have a design. It's a buck converter, so a power supply. The buck converter was chosen because as you see also maybe here in the picture, buck converter are everywhere, so they are the most common used technology for power conversion. And because it's everywhere, we also choose the buck converter. We have a quite common or and really setup where a lot of applications works with. So we have 12-volt input voltage. It's a 5-volt output voltage, so the ratio is not that big. And the output current is around 1 amp. And as a switching frequency, we choose here around 1 megahertz, what is, let me say, in the higher frequency range of the converters. About especially the EMC, we hear it also in the morning from Professor Arturo. There is the electromagnetic compatibility. What we are measuring in the EMC lab, or what we have to do with an application, we have to measure the emission and of course also the immunity. For the emission, there is the conducted emission test and the radiated. Conducted will be from typically industrial 150 kilohertz up to 30 megahertz, and radiated from 30 megahertz up to 1 or 3 or even higher, depending the gigahertz, depending on the clock of your application. Immunity side, also conducted and radiated is possible. So it's like an ESD or an burst, or also coupling with an H field. So these are tests which has to be passed to get in the end the CE certification. Yeah, so for us, and also regarding the point with simulation, I think it fits also very well with the topic from Sven in the morning. Everything has to be faster, and also the faster development times and reduced cost. So simulation is here a good point. But yeah, in some point in time, you have to go to the EMC lab and to do the test, and this is why we also recommend, or we always recommend, to consider the EMI in the beginning of your design. Think about how to place the component, what kind of traces you have, what kind of coupling mechanism you can have. It will cost more or less time, and time is money in this case. But there will be also some crossing point. So when it comes to production, so your prototype passes all the tests, you do not have to do some redesign, then it can produce, and everything is fine. But when you go to the lab in the end and do your measurements, and you find out, okay, there is some coupling, there is some issue with immunity or whatever, and you have to rework your design, place filter, place components which are quite big, and you have to redo the housing and so on, it will cost a lot of money. So I think every EMC engineer and everyone says, consider EMC in advance. And of course, here simulation can help you to get the first feeling and to see how it will behave. So what is the design? So I will talk about the design and how we measure, and Markus will talk about the results later on. So this was, we have two designs, one good and one bad design. So this was we call it bad design. So it's this schematic. We have, of course, input capacitor, output capacitor. We have here also power good signal, but I have to confess it was not working, so it was wrong designed. We have here the inductor, it's a shielded one already. So this was mainly copy paste from the data sheet. When you see the layout, I think most of you will agree with me that the design looks quite poor. So there we have no really wires, no wires fence. We have some quite current loops from the input and from the output capacitor here. Generally, the placement of the components here, C1, C3, are quite far away from the IC. This is not really what we should do. Also, the bootstrap placement capacitor, also the bootstrap capacitor is not really placed well. We have some quite a thin wire which comes through, so the connection is not quite good. And also the ground concept. So we have here no wires connected to ground, so we have no good possibility to filter. So we have here some issue, maybe more. You can also think about it, but of course it will be then also generate some noise. We measured here the EMI, also we measure conducted emission in our EMC chamber. So it's a shielded chamber. We have a conducted wall. We have a table, also a device under test. We have our listen EMI receiver. So we have quite long cable here. So we do not couple with a CDN. We have this the wire, and the wire are placed here with the shape here. And it was a listen from Laudien Schwartz, and we measured after the CISPA 32 here. So when there are some issues with the conducted emission, it could be that because we have our leads from the input, we have our input capacitor here with the ESR of the input capacitor and the parasitics we have in the power supply lines. There will be some voltage drop. And this is what we then measure with our EMI receiver. So rule of thumb would be that the ESR and ESL of capacitor should be quite small, so that the AC component which was taken from the converter do not have to take from the source here. So this could be one root cause. From the radiated emission, we also have a chamber with absorber that we measure the radiated emission. We do not have a turntable in our chamber, so we rotate the design, and also we have to rotate the antenna horizontal, vertical. So this was our device under test. There was some also filter placed here to decouple it, and also another setup was like this to see what is the maximum radiation. But this will not be shown here in this presentation. So for the radiated emission, especially for the buck converter, it's quite critical at the input. So we have some discontinuous current due to the fast switching process. So this is quite critical. And the output, because we have an LC, so this is already in filter. So it's quite it's already integrated, and we have an more or less smooth output signal. Then the second design, so I can also show you we really build everything up. Okay, now it's strange with the background, but we built everything up. So this was the second design. Here we have replaced also possibilities to add an common choke, for example, or ferrites. We monitor the output voltage directly, not over the power good. This is not EMI issue, but this is just for the specification. We changed some capacitor values, so you will see this later on what the effect of this is. And we also changed the output capacitor, but this would be another topic about the stability. But we also improved the design in this way. A few last words about the design that you may understand what we changed. So I said that the ground concept and also the current loops are quite big for this bad design. In the new design, we keep it really short. So when we're looking from the input to the output, and also the capacitor here, it's really compact and short. Also here the ground loop, or the loop what we have. So it looks quite good. And what we did here with the copper and the solder mask, it was a test to maybe to dissipate more heat, but it was not really go well. So is not necessary. Then the last thing about the design before I hand over to Markus is the grounding or the connection from the filter elements and also the connection from the connectors. You see here we placed here wires to have a good low impedance connection, and this is also necessary to have a good filter performance. And yeah, now I will Markus will take over and go into more detail about the simulation and the comparison.
Yeah, thanks, Frank. And then I will share my monitor too. I hope it can be seen. It's updated.
Yes.
Can you see it? Okay, that's fine. So thanks for the introduction and the first part. And we now look at some simulation approaches. We've already heard today earlier on topics about simulation, and you will see there are some similarities, some overlaps, some differences, but it's good for you to get a certain overview about it. And what's the content about this meeting? I first want to make a short overview about the design flow and the methodology which has been used. Again, we will look here at the PCBs, which have been already described by Frank, and we look at the bad and the good layout. We will see how in the simulation also the listen network will be respected. And also I've done an approach that I modeled here a part of the table. You can see it here. This is simulated using a full wave solver, which can handle very large geometries. And also to discuss the effect of, for example, how you put the cable on the table, that you see there is also some effect due to that. Yeah. Then we will have some discussion of the results. You will see there are cases where it matches better or not. Yeah. And I also want to try to give you some impressions, you know, what are limitations, what can be done. We look then and draw some conclusions. And if we have time, then I have recorded the setup procedure that you get an idea about how the setup in such a tool looks like. Yeah? Let's see how far we come. The tool I'm presenting today is from ANSYS, which is called the ANSYS Electronics Desktop. This is a common simulation environment which addresses all the needs of an electronic engineer. That means it has a circuit simulator included, transient, harmonic balance, linear. It has a layout-based interface, and it has also 3D interfaces that you can model arbitrary structures. So what will be addressed here is the tool HFSS, which is using finite elements. This means finite elements, you are maybe familiar with it. That's a more general purpose electromagnetic procedure. And on the other hand, in the package, there is the tool called SI-Wave, which uses a hybrid solver technique, a mixture of 2D FEM and method of moments, and which is specially dedicated for PCBs, which means the usage and the setup is much, much simpler than in HFSS. Then, as mentioned, in that package, there is this circuit simulator. For example, here you see a part of a transient plot, which means you can make the ramp up of such a buck converter. Theoretically, also other RF simulations like envelope or harmonic balance. Optionally, that's not here the topic. It could be also linked to heat calculation, thermal calculations. For example, if parts get dissipated and, for example, due to the heat, you have some feedback. And what also needs to be pointed out as we talk about EMC here in that topic, there is also an EMC relevant library included. For example, if some measurement table should be, let's say, used from scratch, there is an example which could be parametrically changed. Then, for example, certain antenna types or bulk current injection features. So there's a library of even 3D elements that can be used. Let's go back to the circuit of this buck converter, which Frank already has mentioned earlier. And it needs to be pointed out that the SPICE model, here I want to refer to a presentation from Sven this morning, who said that it's really important to have good SPICE models. And from my point of view, this is very often, if you simulate something like that, that's the most critical point, because often we just don't get the SPICE models from the vendor, because it includes their IP. Of course, there are some protected SPICE models, encrypted SPICE models available, but that can't be read with every tool. So in this case, we had a SPICE model of the voltage regulator, which was derived from the LT8610, which means it's not the completely realistic SPICE model, but a similar one, which could have effects, for example, on the transient behavior as well. But this I want to really again point out what Sven said this morning. The quality of the SPICE model is a very, very important point. In a first step, this SPICE model, having just 3 pins, has been entered into a circuit of ideal components. This means at the moment no traces are there, it's just a circuit simulation. And here we see, for example, the ramp-up behavior. That's the input voltage here, 12 volt, output voltage is slightly above 5 volt. Instead of the ideal discrete components, use that's, by the way, here a nice feature. You see, if we zoom in, you see the ripple of the internal switching. And if we use here realistic SPICE components, that means having parasitic elements. I downloaded the components from the Würth website have been used, because all the components there are available as SPICE models, and they can be used inside simulation tools. And then you already see some different ramp-up behavior due to some parasitic effects in the model. But this approach shown here on these slides does not yet show any parasitic effects due to PCB layout connections. So let's have a look at the design flow, which is presented here. So we import from third-party layout tools the layout. And there was also one question this morning, can, for example, Gerber file be used? Theoretically, yes. But the usage of a more advanced file like ODB++ or IPC 2581 gives much, much more possibilities, because in these files, there's not just the geometry, but the information, what a plane is, what a trace is, what a pet is, and also where a component is placed is all included. This means a simulation tool can make use of this information on a much higher level, which means it takes much, much less user interaction. So if you have the possibility, please go with ODB++, IPC 2581, or use of one of the direct translators from vendor tools into such a simulation tool. In the next step, based on the setup, which will be explained a bit later, the S parameter or SPICE model will be extracted. Here we see a plot of the S parameters over frequency, coupling, insertion loss, return loss. And this means it's the data representing the broadband behavior. With a full wave solver, we can simulate up to several gigahertz. That's no restriction for the upper frequency. But this model needs to get extracted. Then we already have seen, okay, there is an existing circuit, and this now needs to be combined. That means the electromagnetic model will be embedded into the circuit. I've done it here. I've split up, this box here, which you see is the PCB. And for example, here I've used some external SPICE models, which are placed there inside at the PCB. So this is merged together, the circuit and the extracted electromagnetic model. Then, of course, we run again a transient analysis, of course, embedded with the electromagnetic model. And I also want to point out the electromagnetic model can also include parts of the measurement setup. We discuss it later, the cable, for example, or if you do a radiated emission, it should, of course, include also the receiving antenna. Then this is all part of the electromagnetic model, because the loss between the radiating object and the receiving antenna will then be included also in this electromagnetic model. But this needs a full wave solver then for sure. Otherwise, the radiation could not be taken into account. Then a Fourier transformation will be made from the circuit. This means at every point where a port of the circuit simulator is connected to a port on the printed circuit board on the electromagnetic model, the signals according to magnitude and phase will be handed over after the Fourier transformation to the electromagnetic solution, and then can be used, for example, for a current visualization, like visualizing the currents if the switching active device would be there, or watching, for example, the radiated field. In this case, for example, it's a near field in 3-meter distance over frequency. Yeah? This means every frequency point then needs to be solved, and the radiation from the board or the device under test will be kind of evaluated, yeah, either with antenna or without, or just by calculation from Green's function. This is the design flow. Short introduction about this method in HFSS, in the high frequency simulation structure solver. Here we use an auto-adaptive mesh refinement, which is a very essential feature, which means the user does not need to have any mesh expertise. The example is, of course, here an antenna example, which maybe doesn't fit very well, but the principle can be seen. So based on a geometry, an initial mesh will be made, which can be coarse and is just related to the geometry. Then, based on this initial mesh, a lambda refinement will be made. This means the software checks that the size, the maximum size of the element versus wavelengths is just a certain fraction. The energy injection at the ports will be solved, and then the first solution will be solved as a differential equation matrix. Then the question, has a defined convergence goal be accomplished? In the first pass, it's not possible. This means some refinement will happen. The mesh will be refined in certain areas where the local energy error is the highest, and this will go through in a loop until the mesh is refined or converged. Typically in those areas where the E-field gradients are the highest, there you have the strongest refinement. Yeah? And then the broadband solution will be done. Yeah? This is the procedure about this auto-adaptive mesh refinement. Now have a look here at the example cases from Würth. So here, this has been imported, in this case from Altium. There is a direct link to our native geometry format, EDB, electronic database, or you can alternatively use ODB++. Yeah? And also here it's really essential to look what is included in the layers. And I want to repeat, to have a clean design is very, very helpful in the beginning. Yeah? So this is then the imported geometry, which can be looked at in the simulation tool. The next is that ports need to be defined. This means it's kind of the counterpart for the measurement points where you measure with a network analyzer, calibrated network analyzer. And this means at different points, ports need to be placed, for example, here at the DC input, at the load output, and eventually also at some components here in the chip, at some pins in the chip, and eventually at some components here on the board. This really depends a bit on the frequency range, because imagine if you do an analysis at several hundred megahertz and you have let's say a shunt capacitor of 47 microfarad, you can imagine that this is almost an entire reflection. Yeah? So S11 will be close to 1 in that case. Yeah? And that could cause instabilities in the simulation. Yeah? For very large shunt capacitors, it's sometimes beneficial to have this outside as a port. This is here, for example, the mesh, which got refined. You see in the area of the transmission lines, the mesh looks good. Here in the area of the emblem, where the field strength is very low, there is almost the initial mesh. This means almost no refinement has been made, but it's not necessary for the S parameters. Yeah, this is here the convergence, better than 0.5%. And this is the extracted S parameters, which has been used here, which shows also some resonance effects. In this case, up to 100 megahertz. Let's have a look at the two concepts of the PCBs, which Frank already has mentioned. Yeah, what needs to be pointed out? So the bed layout has really just a few vias for connecting the upper and the lower ground. You see here, there's the upper ground, underneath there's the lower ground, and there are just, I think it's just two vias. Yeah, it's intentionally. Yeah, which causes some additional current return path, generating additional inductance. The good, you see, so it's likely that it causes also resonances and of course a high inductance in the ground path. Yeah. The good layout looks completely different. You see, you have a via fence, you have vias nearby the traces and also near the switching part. So this is really much, much better. And it has a lower inductance. Yeah. So here in this case, the extracted board has been here split into several blocks. Then the SPICE models from the Würth website have been placed there. And here we see the input 12 volt and then some voltage measurement positions where we can monitor the output. And so it's important to have, of course, the accurate SPICE models to have the correct behavior. And as I mentioned, especially for the very large shunt capacitors, it's helpful to have these LC elements or the capacitors not directly inside the electromagnetic model, because this would cause almost a short circuit, and to keep it externally. A further advantage is that then it's possible to exchange the SPICE model by another component, what also has been done, and study what capacitor or what capacitor family has a better effect for the suppression of EMC, of conducted EMC. Then some transient setup here, in this case up to 20 milliseconds with a spacing of 5 nanoseconds has been set up. And you see that's the ramp up of the bed layout. The load is 4.7 ohm. You see here, this is supply voltage, and here at the load and the output of the IC, that's the blue and the red curve, which is almost on top of each other. And this is here the good layout, which has a different ramp up. And you see also here that also here is a stronger ripple visible than here. And such a analysis could, of course, not be accomplished without the electromagnetic model included. This means just based on a entirely SPICE circuit, just including the RLC components, it would not be possible. Let's have a look how we more can come closer to the measurement. Yeah, a LISN, a line impedance stabilization network, has been used from Rode and Schwarz here in the measurement setup. From the data sheet, you can get some internal data. There is a receiving port where we have the output to the test receiver, which means it's the counterpart also we want to look at in the simulation. And this has been modeled also as a circuit. It's flipped around. Here the output is to the left, here it's to the right, and goes to the emitter under test. And here we have the receiver terminal. Yeah. There is, by the way, also a library available of LISN models. This means you can choose. It has, of course, some standard device values included, but it could also be changed. Then I also want to point out what I said earlier. An interesting point is to raise the question, what's the effect of the measurement setup in the EMC lab? And you see, for example, here on the photo, on the image, which already Frank has shown, we see here the device under test. And here we see the cable. And here's the LISN. That's the device from Rode and Schwarz and the supply network. Here's a zoomed size of the cable setup. And the question is it beneficial, or what is the effect of, for example, of of the cable, of the positioning of the cable. Yeah? And this is a question which also can be answered by using 3D electromagnetic simulation tools. And I did a trial, and you will see this later on in one of the slides if it comes to the question comparing with this setup, with this cable setup, or without the cable setup. You will see there is an effect. Yeah? The major reason for the effect is that we have here some loops in the cable. Yeah? And you can imagine, if you look at the classical approach, for example, current goes one direction here and back here, we have some area in between which allows that some H field gets built up, some magnetic field. And stored magnetic H field always means there is an inductance, yeah? And this is very obvious. So the question is finally, what is the effect of that cable by means of adding some inductance here? And I've made a similar model. It's of course not the same. Yeah, we could of course play a little bit around. I made here some spacing in between the cable, but that it looks somehow realistic, because we don't have the geometric information how the cable has been positioned. But it's about 1.5 meter in the length and has been positioned. Yeah? And in a first approach, I used a quasi-static simulation tool, which allows directly to look at the inductance. This means at both ends having terminals, so 2 terminals here, 2 terminals here, and just looking at the inductance. And you see, this is by the way a bit a spread here, that the inductance is around 2 microhenry. Yeah? Which changes a bit over frequency, but which means if you imagine that you have some spectral contents, maybe around 10, 20, 30 megahertz, you can imagine that if goes through the cable with 2 microhenry, that this has a certain effect on this. Yeah? And I often spoke to EMC engineers, and they also said sometimes, you know, if you make a measurement on Monday, sometimes it's different like you make it on Tuesday. That might be such an effect if you don't really pay enough attention to the positioning of the measurement cable. If we look at the corresponding insertion loss, this means the S parameters, we see in this case that there are some losses which can be observed, yeah? Which is quite strong, and you will see it at the spectrum as well. Yeah? But let's go back to the PCB first. So this is here the bad version of the PCB we used here. And here the goal was compare different capacitors from Würth in this case. Yeah? So here it was an Aluminium Electrolytic capacitor out of that series, 47 microfarad. Of course, you see there's a certain tolerance, which also always needs to be taken into account if you compare measurement with simulation. Yeah? It's not completely fixed, and there's always some variation. So this is here in this case the measured setup, and this is the simulated setup. Yeah, we see both are very close here. The peak basic switching frequency to about close to 100 dB microvolt, and then it's going up. We see here a bit more a maximum around the area of 10 megahertz. There are some differences, but let's say the trend is similar. Yeah. Always, again, please keep in mind there are differences in the model typically between what you simulate and what you measure. Yeah. If we now take into account a different capacitor, this means it's an aluminum polymer capacitor, also 47 microfarad. Yeah. Then we see also that here, both in the simulation and the measurement, the shape changes a bit. Yeah. And is here significantly less in that case. This means that this capacitor is capable of suppressing here the conducted emission level to a much better extent than the first one. Yeah? So this is a kind of comparison which can be done very well, and which is a huge benefit because this doesn't need time, especially if the capacitor is put into the external circuit. Then it can be exchanged very fast, and the simulation just takes really a few seconds. Yeah. Here for the good board, we have noticed there is some remarkable difference. Yeah. You see here the major spike is around 32 dB microvolt. Here it's about, too optimistic, it's rather 20. Yeah? That's something which is at the moment a bit difficult to estimate. We see there are differences, yeah? And that's something we need also further to investigate further and check eventually if maybe some either parts of the board or of the measurement setup have not been respected correctly. Yeah, but I want to show you it's sometimes it's even realistic that you see stronger deviations. Yeah, it's a learning curve you typically have to go through. After applying the Fourier transformation to the board, we can look, for example, here at the current density, for example, here at 10 megahertz. And we see here the bad design, the current density on the board has, of course, the strongest centrifugation here around the switching device, but also here along the transmission lines in and out. Yeah. If we compare it with the good design, having the same scale, you see here in the outside, it's almost completely blocked. Yeah. There is still some current here in the area of the decoupling capacitors, yeah, which is all right. But you see here the input and the output line is clean. Yeah. And you could go through all the different frequencies you have solved and look, really study and investigate how the current distribution looks like. And this is what I want to show you here, the comparison of the setup with cable and without the measurement cable. Yeah. And this is what I mean by adding these 2 microhenry or respective the inserted S parameters, which you have seen. Yeah. There is a quite strong deviation depending on what you're doing. Yeah? And you can be sure if you put the measurement lines closer to each other, this means the induction gets reduced a lot, then the deviations will be not so strong as it can be seen here. Yeah? That's, by the way, something I think you can also reproduce quite easy in the measurement setup by yourself if you play a little bit around and try to study what the spacing between the measurement cables, what effect this has. Yeah? So here in this case, it's maybe a bit difficult to simulate what you have. Yeah? And that's something which should be considered. Just a short outlook. Yeah? If we talk about decoupling capacitors, there are optimization algorithms available. For example, in the tool SIWave, where you have fixed positions, but you can choose from a library different candidates of decoupling capacitors. Yeah? And then some genetic algorithm gets started and you enter a target function for the target impedance. This means which is the impedance which a consumer, like an IC, is seeing versus the voltage regulator module. And then the candidates are getting optimized from the different families of the vendors, and you can see how you can, with the best choice, accomplish the target impedance. Yeah? That's just a short outlook, and I'm finished quite soon. This means, as a summary, if we want to make such a simulation, it's really essential to have an accurate SPICE model, and have a, let's say, a correct board geometry, because otherwise it's really it doesn't make sense to rely on such a simulation. And in general, if you have a good SPICE model, you can, or a good circuit models, you can enhance, of course, the accuracy. If you add like electromagnetic parasitic extraction of the traces, pads of the board itself, sometimes you have resonances on a board, which can be then detected by a full wave solver. If you have a board imported, you can either use it with embedded models. This means the RLC components are part of the electromagnetic model. Or you can have the passive circuit elements like these decoupling capacitors externally, what I've shown you. Yeah? The advantage, if you have the passive circuit elements externally in the circuit simulator, then is you can very fast and easy change this and study the variational effects of changing the devices. And then if you want to increase the accuracy of the simulation of this conducted emission in this case, think about containing also a physical model of the measurement setup, of the table, of the listen network. If you want to simulate radiated emission, take care that you have a model of the antenna, of the receiving antenna if needed. Yeah. And what can be studied very well, even if you're maybe not on an absolute accurate level with the simulation, because there is maybe some offset, you can very well analyze changes in the layout or in the change of components. Yeah? So that means a relative change of parts of the printed circuit board is something which can be analyzed very well and very easy, even if maybe the absolute value of the emission is not fully correct. And then I want to point out that using optimization methods, that's the advantage also of simulation tools where you can parametrically change discrete components or optimize it, that you also can do a design improvement based on this. I'm finished from my side with the presentation and say thanks to your attention, and maybe we have some questions we can discuss.